Hello there and welcome to Lower 6th Further Maths A-Level Pure Core 1 Past Paper in 2016, and here we have question 7 from an old FP1 paper. So, prove by induction that the sum of, so it's a quite complicated one here, 2r plus 1 over r squared r plus 1 squared equals 1 minus 1 over n plus 1 squared. So let's set ourselves up with lots of space here and start at the first part for proof induction. Prove true for n equals 1. So the sum of 1 to 1 of this expression here is going to be 2 times 1 plus 1 over 1 squared times 2 squared. That will give us 3 over 4. And on the right hand side it's going to be 1 minus 1 over 2 squared. That's 1 minus a quarter, which is 3/4. Great, so that's proved the first part. Second part is assume true for n equals k. So the sum from 1 up to k of 2r plus 1 over r squared r plus 1 squared equals 1 minus 1 over k plus 1 squared. Great. So now part 3, and this is the more difficult bit. This is prove true for n equals k plus 1. Right, so what we want to show, WTS as always, is the sum up to 1 from k plus 1, or the other way around, 2r plus 1 over r squared r plus 1 squared equals 1 minus 1 over k plus 1, so plus 2 squared. Okay, this is what we want to show. So let's start with our left hand side, and this is going to equal the sum from 1 up to k of 2r plus 1 over r squared r plus 1. So we've added up all the expressions up to k, but we forgot about the k plus 1 bit, so I'll include that now. So 2 bracket k plus 1 over k plus 1 squared, and then on the bottom it's also k plus 2 squared. So what I've done here is I've substituted k plus 1 into this formula here, because those are the items, those are the expressions that I'm adding up. So what I can do now is I can use the formula for the sum up to k in my part 2. So that's going to be 1 minus 1 over k plus 1 squared. And this will then add on to 2k plus 3 over k plus 1 squared, k plus 2 squared. Times top and bottom by k plus 2 squared, so k plus 2 squared over k plus 1 squared, k plus 2 squared. The reason I'm doing this is to create a common denominator in both of my terms. Okay, so now that I've got common denominators here, I'll expand the middle expression and then take away. So 4k plus 4. So all of this part of the fractions is going to be subtracted. And all this right-hand expression is going to be positive. So combining this, what I'm going to have is 1 plus minus k squared, and I'll have minus 4k added 2k, so that'll give me minus 2k, and it's will be minus 4 add 3 will give me minus 1 over k plus 1 squared, k plus 2 squared. So now this is going to be 1 plus, if I factorise out the negative, and it would be k plus 1 squared. You can see that if you get rid of all the negatives, then it would just be k squared plus 2k plus 1, and I can simplify that to k plus 1 all squared, which will leave me with some cancelling to do. So I'll pull out the negative to the front, so it's 1 minus, and then cancel out the k plus 1 squared, and I get 1 over k plus 2 squared. Excellent. So what this gives me is left hand side equals right hand side on the want to show for part 3. Great. All that's left to do now is to write out the conclusion for part 4. So I'm not going to write it out, you can save some time by looking at the mark scheme. For all values, given that we have proven true for n equals 1 and assuming true for n equals k, we have proven true for n equals k plus 1. Therefore, by mathematical induction, our theorem holds true for all values n existing in the positive integers. Make sure that you remember that n has to be a number in the positive integers. If n was something like a half, it would not work. Okay, 5 marks for that.